video, but I couldn't. So, hi office hours. We just had a little chat. I forgot to start the video while I was chatting about how the midterm didn't go so great. And essentially what's going to happen is I'm going to, for everybody, I'm going to calculate your grade two ways. And I normally do this, but for this class, I usually don't announce it to the class. But for this class, with how that midterm went, I have to. I just want to let you all know so you don't, when you see the midterm, I don't want you to be so crestfallen that you think there's no hope, because there's still hope. Midterm 1 is 15%, midterm 2 is 20%, final is 30%, homework is 20%, nope, lies, homework's 15%, lab is 20%. So this is the normal grade distribution that we have that's outlined on the syllabus. With how bad this midterm went, I'm willing to do this. Midterm 1, 15%. Midterm 2, we'll change color so it's more dramatic. 20%. Sorry, that's not change. 10%. Final, 40%. Homework, 15. Lab, 20. So essentially what this does is it gives you another opportunity. Essentially we move most of the importance of this midterm into the final to give you another opportunity to show that, like, no, you actually can do buffers, you can do titrations, you figured it out, it just took you an extra 2 weeks. But you got it, and that way, even if you completely bombed this, even if you skipped this midterm, like completely skipped it, it still would not have a huge impact on your grade. I mean, 10% is not nothing. It can drop you a letter grade, but this could drop you 2 letter grades, right? So it's going to reduce that impact a lot. We're also doing another quiz. So the reason we're doing another quiz is because that'll put us at almost 8 quizzes this quarter. If we do one this week, and then we do one week 9, one week 10, that'll put us at 8 quizzes this quarter, which is the most quizzes I've ever gotten in one quarter. And I will drop the lowest 2 quiz scores, right? Because I only need 6 quizzes to really get a good quiz score. So that's trying to bump up this homework grade as well. So that's part of the reason why I was like, okay, we're going to do another quiz. This will make it so if you bombed a previous quiz, like, we can erase that, essentially. So I'm trying to find ways where we can bump this up and make it so the performance on this midterm doesn't have a big impact on your overall grade. That's my goal. And there's limits to how much I can do, but I think this works within what I'm comfortable with and gives you enough opportunities. Questions? Yeah?
Is there a curve in addition to this method?
Yeah, so in addition to this method, I will still curve your final grade. So with both of these, I expect my averages are usually 72%, right? I mentioned earlier that the average on this midterm was closer to a 50%, which is really, normally my average ends up being a C+, B- range. Now there's a limit to how much I can curve this. If the class average ends up being a 50%, just fail half the class. I don't want to do that. I'd rather the average end up being an 80% and I just give A's to half the class. That's my preference. But with what I'm seeing on the midterm, I'm more worried about the first thing happening. I'm worried about it, but I'm trying to find ways where that doesn't happen. The average ends up being about what I expect, and we get a good grade distribution. In terms of where the D plus C minus is, that's going to depend on the standard deviation. And the problem is, the standard deviation, while my averages are really regular throughout different quarters, the standard deviation can be really variable. So that really has a lot to do with how students performed at the beginning of the class, how well they had information coming in. If I end up with like a really broad distribution, my standard deviation ends up being larger. And if I get a little bit more of a narrow distribution, my standard deviation ends up being a bit smaller. It's usually somewhere between 5 and 15 percentage points. It's a pretty large spread. Another likely thing to happen is we end up with what's called a bimodal distribution. So we get a group of students that are not doing so great, a group of students that are doing really well, and the average ends up being between them. Right now, what it looks like, we've got almost a trimodal distribution, which is to say there's a group of students that aren't doing well, there's a bulk of students that are doing okay, and then there's another bulk of students that are doing really well. But it's pulling the average down kind of below where I want it to be. So hopefully doing extra quizzes will help smooth out this distribution, bring more people towards like a middle score, and shifting to the final and having people do well on the final will also smooth out this distribution. And having all of this together is why I don't actually make a curve until the end of the quarter, because each individual thing is kind of spiky and chunky, but when you take them all together, you get something nice. Question?
Can the lab help our grade at all?
Yeah.
Okay.
Yeah, the lab is worth 20% of your grade. I'm not going to modify that. That's a pretty standard, that's pretty department standard. Lab's 20%. Average in lab is usually around 75 to 80%. And those lab grades are normalized between the different classes. So if there was like one easy class and one hard class, the easy class might have their score bumped down a little bit, and the hard class might have their score bumped up a little bit, so all the classes have the same average. So if you're like, but my instructor in the lab is just really hard, like, no, it all gets averaged out. So, yeah.
When will midterm grades be posted?
Today after class. So I'm going to hand them back in class today, which I'm worried about, but I'm going to hand them back in class today at the end of class. And then I'll make them available online so people can make sure their scores matched up here and then there.
So is it going to be like if you do better on the finals method too, or
Yes.
going to do method 2?
If you do better. So I'm going to do both these calculations and give you the better score of those two calculations. My guess is this is going to be the better score for almost everybody. Almost everybody. Not necessarily everybody, but almost everybody's going to benefit from method 2. Question in the hall.
Are you able to tell us the average?
50%. Yeah. I will say there was one problem. I'm gonna change the midterm to be out of 63 points instead of 65 points because everyone got problem 8 wrong. And I realized I made it being like, this is a little tricky. We'll see what happens. It was the what dictates the acidic behavior of metal hydrates, and the choices were increased charge, increased radius, electronegativity, and some other nonsense thing. And most people went with increased charge and increased radius. But it's increased charge and decreased radius. So the only thing on that list that actually increased acidity was increased charge. And no one picked that. A lot of people, and that was option A. A lot of people picked option B, C, and a couple picked option D, but no one picked option A. I don't know why, but yeah. So I'm just gonna toss that question out, even though I think it's a completely fair question. I'm gonna toss it out. Midterms out of 63 points. But yeah, the average is still low enough that if I were to try and make a curve for it, I couldn't curve that low and be comfortable with it. And part of the reason I'm like, oh, is because it's very similar to the midterm I gave in spring, and the average on the spring midterm was much higher. So I'm like, wow, I don't know what I did wrong. I don't know what I did wrong. I assume it's my fault. Yeah.
Was it the same free response problem?
It was a different free response problem. It was a different free response problem. Depending on who you asked, their free response problem was arguably more difficult. It was acid-base equilibria with a precipitate involved. So kind of like what we had on our first midterm, but like the last part C that I didn't actually ask you to solve. Yeah, she needs to get into that drawer. Yeah. So, other questions?
Can we go over how to do the midterm problem? Just because, like,
Uh-huh.
on the video, I feel like that was mostly like assumptions and ranges, but I didn't.
Yeah. So we can do that. So the video I showed you was for that mentality. It was essentially the thing I wanted to stop and say to everybody. Like I wanted to go up to like 10 different people that I could tell were stressed, that I could tell were like they were staring at the free response problem and they had like nothing written down, and I just wanted to be like, look, think about what you know about titrations. What do you know about the midpoint? What do you know about the equivalence point? What context does that give you for understanding this buffer? Because it turns out with those approximations, 30 milliliters of strong acid, 125 milliliters of the weak base, that's pretty much the right answer. Like you can get really close, and then if you do the 4/5 thing, 80% of the equivalence point is the buffer capacity. About 40, like all of that's pretty much the right answer. So then the question becomes, how do we do it actually the right way? So this will also help us out for the quiz today, and it is essentially the lab and on one of the homeworks, and partly was on one of the homework quizzes. Yeah.
Just to confirm, the quiz is only on this buffer check
Yep.
calculation?
Yep. That's all it is just a buffer problem. So let's see if I can remember this. We got 0.4 molar stock. Weak base. We've got 1 molar HCl. We want 250 milliliters at 0.2 molarity. That's for our total concentration with pH equals 7.23, and this had a pKa of 7.4 something. Let's just say 7.43. That's close enough. That's a weird looking 3 though. Oh, that's not better. So, let's do it just the way that the lab has us do it. And you can scoot in, someone can take my chair too. So if we do it just the way that the lab has us do this, we say 7.23 equals 7.43 plus log B over BH plus, right? I think it was 4.1. Because I know that you should get negative 0.18, and then you take the negative log, or then you put that to the power of 10, you get like 0.6601. So you go ahead and you do that. You say 7.23 minus 7.41 to the power of 10 is equal to concentration of base divided by concentration of HB, keeping in mind that this is at excess or at equilibrium, depending on how you want to think about it. But since we're using the excess small approximation, the excess concentration is the equilibrium concentration. Calculators out if you can give me a hand. I think this is equal to 0.66, but I just want to make sure I'm not remembering things incorrectly. 0.66? And if we want to keep extra digits, it's 0.6601. Concentration of B at excess divided by the concentration of, let's move this over. Equal to concentration of B at excess divided by concentration of BH plus at excess. And then we also know that 0.2 is equal to the concentration of B at excess plus the concentration of BH plus at excess. You could also, like I said earlier, you could call that B initial if you wanted to think about it in terms of the ice table. I like to think about it in terms of the stoichiometry, so I'm thinking about the end of the stoichiometry table, which is also the beginning of the ice table with the way we set it up. We can do a substitute and solve. Let's see, I think it's easier to do the substitution this way. 6601 BH plus is equal to B. And then we get 0.2 is equal to 0.6601 BH plus BH plus, right? So I just moved this over, plug in my BXS. This is going to give me my concentration of BH plus at excess is equal to 0.2 divided by 1.66. I can't do that in my head. .12 molarity. And then I'm going to do 0.2 minus 0.12 to get my concentration of B at excess. It's 0.08 molarity. Yeah, so this is 1.66 times B. So just factor the BH out 1 plus and divide it over. If I take these two numbers and I plug them back into my Henderson-Hasselbalch, I should get, you know, if I say what's this value, if I plugged it back in there, I should get 7.23. Right? And I could do that check if I wanted to make sure I did it correctly. But that just tells me about my kind of excess equilibrium situation. And now I have to say, okay, but how much do I start with to get there? So we have to remember a couple things, right? And this is a little bit reversed from what we did before because we're doing a weak base with a strong acid. But my concentration of, let's do this. Let's do it in terms of moles. My moles of BH plus at excess is equal to my moles HCl I add in, right? That's going to be thinking about where can I erase. I'm going to erase the problem at the top so I can write the chemical reaction we're thinking about. I think we've got all this information taken care of. So the chemical equation that we're thinking about here is B plus HCl goes to BH plus. Oh, we can do it like this. I like this better. H3O plus goes to BH plus plus H2O. Right, where this H3O plus is the HCl. So I'm thinking about the moles here. Moles here. 0, 0. Let's call this moles HCl. I know my moles of HCl is going to be my limiting. So minus the moles HCl, minus the moles HCl, plus the moles HCl, and I don't care about water. So notice the thing that's important about this, that's 0. Notice my moles of BH plus is equal to the moles of HCl I added. So that's the first thing. Second thing is the moles of B at excess is equal to moles B start minus moles HCl added, right? So I've got the moles at the start minus the moles of HCl added, and that's going to give me B at excess. What am I writing? BH plus at excess. Right, so this is what I'm calling number 1. This is what I'm calling number 2. This was 2 of the important shortcut things that I said we needed to remember. So the other thing you can think about, the other way, we can rearrange, we can use number 1 and number 2 to do a little funny rearrangement. I can pull this moles of HCl over, and then convert it to moles of BH plus. So I can say that the moles of B at the start is equal to the moles of B excess plus moles of BH plus at excess. And this should not be a surprise to anybody, right? Because all this tells us is all of my B after reaction, all of my base after reaction comes from the base I started with, right? Just the conservation of matter, stoichiometry, everything I start with becomes the stuff that I have after all. The thing that's nice about that is it allows me to say that the total number of moles is going to be related to the total concentration, which I have right here, right? And again, the moles, because we're all in the same volume, the moles and the concentrations are going to be somewhat the same thing. Because if I divide everything by volume total, I'm going to have my molarity of B at the start is equal to my molarity of B excess plus my molarity of BH plus excess, where I know that this is 0.2. Right? And I did this on the video in a bit of a quicker way, just being like 100%, 50%, 0%, right? I looked at it just in terms of what we understand about titrations. But if we didn't understand that and we just did it from the way that I find the way the lab does it a little bit more obscure. And I feel like there's easier ways to do it, and that's what I was trying to show in the video. But this is the way the lab does it. This allows us to start to get to the actual answer. Which I'm going to leave Henderson Hasselbalch. I'm going to erase this other stuff, the calculations, except for, I'll leave that bit for now. So the final part that we need to do in order to get our answer is 0.12 times 250. It's going to be equal to our moles of HCl. And then moles of HCl divided by 1 molarity is our volume. So moles of HCl, because it's I tried to make it nice, making it a 1 molar HCl solution, so that your volume and your moles were the same thing. So that's your moles of HCl that you need. And then we're going to do 0.2 times 250 equals the moles of base that you need. Whatever the base is. I can't remember what base I used right now. Yeah.
Would it be, is it 250 milliliters or 250
Oh, yeah.
milliliters?
I was doing the millimoles just out of habit. Yeah, we can do 0.25 equals the moles equals the moles. And then you can do moles of B times, let me think about it, 1 liter per 0.4 moles. That will give me the volume I need, and the same thing for HCl. I'm going to do moles of HCl times 1 liter per 1 mole. And that'll give me my volume of HCl. I'm going to make sure I didn't make any mistakes right now and see if I got the right thing. 0.2 times 250 divided by 0.4. Yep. 0.12 times 250 divided by 1. Yep. Notice I could have written this expression in blue that I just did a little bit of a different way. Because really this is an M1 V1 equals M2 V2. And this is an M1 V1 equals M2 V2. Right, and the reason that works is not because we're doing a dilution, but it's because we're looking at things where the moles are equal, right? I want the moles in my solution equal to the moles of the material I'm adding. So I could have done both of these as just a, if I wanted to simplify, I could have done this as in my back pocket. 0.12 times 250 equals the volume of HCl times 1, because that's the molarity of the HCl that we're starting with. And then I could also do 0.2 times 250 equals the volume of base times 0.4, the molarity that we were starting with. right? Because the moles in my solution, in my buffer, are equal to the moles that I added, and the moles in my buffer are equal to the moles that I added. Part A, done.
I have a question.
Yeah.
So when you do 0.12 times 0.25, you get 0.03.
Mm-hmm.
Oh,
Right. So that's how the background of the buffers lab did it. I think using our modified Henderson-Hasselbalch equation is a little bit easier than that, because there's, in my opinion, less to keep track of and less kind of additional considerations to have. Do you want to see that method as well?
Sure.
Okay. I needed at least one person to say yes, otherwise we'd just move on.
Wait, I'm actually so confused.
Okay, no, let's
If you
get this.
do- if
Please
you do-
ask your questions, because I think a lot of you are, I think a lot more people are confused than people are letting on.
Because if you do 0.12 times 0.25, you get to the moles of
Uh-huh.
HCl, which is 0.03.
Let me double check.
And then if you times it by 1, that's 0.03.
Yes, then divide by 1,000, you get 30 milliliters. Or sorry, multiply by 1,000, you get 30 milliliters. And that should be, it should be 30 milliliters.
Yeah.
Approximately. I might have a rounding error someplace. But it should be approximately 30 milliliters.
Wait, so the quiz today, it's just on this, right?
Yeah. But I changed the numbers.
Right.
Of course. Still doing the week base one, though. I think that might have been too much information. But
Okay.
if you're in office hours or watching office hours, you know now it's a week base. So, how could we do this if we wanted to just simplify and use the modified Henderson-Hasselbalch? I'm going to erase some of this if that's okay. I'm going to write down my modified Henderson-Hasselbalch right below it in blue. We're going to have the same kind of expression, 7.23 equals 7.41 plus log. In this case, we're going to have 0.2 times 250 minus V divided by V. Solve for V. Right, so what I did here was I'm using the fact that my moles of HCl here is going to be the volume of HCl times the concentration, which happens to be 1, which is why there's just like, it's just V. So this is going to be minus V times 1. This is going to be minus V times 1. And this is going to be V times 1. How is that green showing up? My green is fading. Let me sneak in here real quick. So that simplifies things. Actually, I got it right here. So that is where, and you can see the moles of HCl that, sorry, not the moles of HCl, the moles of V that we're starting with, because of the total concentration is 0.2 times 250. Now notice this is just to solve for the volume of acid we would add. To get the volume of base we start with, you just do an M1V1, M2V2, right? The same thing that we did before. Recognizing that what matters is not the concentration, but the number of moles. And what matters is the number of moles I have here. And how do I get that number of moles? Well, I have to add that number of moles. So if you solve for V this way, you should get 30 milliliters. And then you also need to do the 0.2 times 250 is equal to 0.4 volume of base. Where these, where to put my other pen?
Times 0.250, right?
Yes. Or if you leave it as 250, that volume will be in milliliters already, which is kind of nicer. Millimoles, it's great. And this would be the volume of HCl. This would be the volume HCl. Where I've just left off the times 1 molar because I made it. I tried to make it a nice problem. So I find doing it in these two lines easier than how the background of the lab did it, but it takes more understanding of the chemistry and more understanding of the concepts in order to do it this way. Yeah.
Wait, so inside the parentheses, it's 250, not 0.25?
Either way, if
Then
you
you
do
switch
it in
milliliters.
250, then your volume will be in milliliters.
Okay.
If you do it as 0.25, then your volume will be in liters.
Got it.
So
Right.
we can do that because it's just a ratio, right?
Yeah, because it's a ratio, the total volume is going to cancel out, and we can do everything in the parentheses in terms of moles. And that's one of the shortcut tricks that we learned about 2 weeks ago. Notice this is, while I think this looks easier, technically you're still doing all of the same stuff. We're just condensing it into one step rather than thinking about it in 3 steps. Right? We're still using both this number 1 and this number 2. Number 1 is what lets us write VHCl here. Number 2 is what lets us write this thing on top. Right? All of that's there. Look, moles of B start minus moles of HCl added. Like, it's all the same stuff. It's just condensing it. Question?
When you do 0.2 times 250, doesn't that get you the millimoles? So
Yes.
Is the 250 supposed to be in parentheses with the VHCl? Or how come you can subtract like a volume from the
So
mole?
keep in mind, the reason this works is because this volume HCl is times 1 molar.
Oh, okay.
So I just left off the ones here. I could have had
Oh, so that's still
times
moles.
1,
Okay.
right? Times 1. I got sloppy with my notation. Yeah.
And then to find the other volume, you just do the M1V1.
Yep.
With that. But with the volume we find there.
No. So the volume we find here, so essentially we have to do 2 calculations. A calculation to find out how much HCl you start with, and a calculation to find out how much base you start with. And those are 2 separate calculations. And notice we can actually do these calculations separate from each other because they both depend on the number of moles of base you start with. And the number of moles of base you start with is defined by the problem as 0.2 times 250.
Okay.
So recognizing that 0.2 times 250 is our starting moles allows us to split into this kind of like simple thinking. The longer way, the first way we did it, really walks you through to get to this idea that the moles you start with is equal to the moles of the other stuff. And gets you to this idea a different way. We good?
Yeah.
Yeah.
Where's the 0.4 come from?
So the 0.4 was defined in the problem. I erased it because I needed more space on my board. But the 0.4 was the starting concentration of our stock base solution. So it is concentration of buffer times volume of buffer equals concentration of stock times volume of stock.
Do you even have to do that if you know how much HCl to add because it tells you have to have 150 milliliters of this stuff?
Yes, because it doesn't actually tell you how much stock you have. It tells you want 250 milliliters of the buffer total.
But if you have how much HCl you put in, wouldn't you know how much buffer to put in?
Not if you add water as well.
Oh.
So there was probably about not quite a dozen students that found the volume of HCl and just did 250 minus that. But that doesn't take into account any dilution with water, right? And to get a target concentration, we need to take into account dilution with water. Yeah, you can always add water. So you find to get this concentration, you only put in 125 milliliters of stock and 30 milliliters of strong acid. So that only gives you 155 milliliters. And then you add another 95 milliliters of water to get to your 250 total. And the difference there in the way we think about it is, are we thinking about it in terms of the moles that are present, or are we thinking about it in terms of the concentration we want? In terms of all of our stoichiometry, we just care about the moles that are present. but our final solution asks us to think about the concentration. So that's where we add the extra water. And no place in the problem does it ask you how much water do you need. Because if we were doing this in lab, you just put all of your stuff, and you remember, you did this in lab. You put all your stuff in, then you fill to the 250 mark, right? You fill to the line. You didn't have to, like, I'll admit, the first time I taught this class, I tried to do a calculation where you had to, like, get the right amount of each thing to get to 250 milliliters from the base things, from the starting materials. But it turned out you had to, like, it was the wrong way to do it. But it was like, the way I made it work was you had to find the concentration of HCl needed to get the right volume. But that just means you're diluting your HCl rather than your buffer, which is not, in the calculation, is way harder. And I felt like such not a jerk, but like I definitely showed my class, like, here's one way you could do it, and it was like the hardest way you could do the problem. And I took like a whole class to show them that. I was like, isn't this neat? And they were like, no. And I was like, actually, yeah. And then it was like a week later, I was like, yeah, that's not neat. So, that was part A. Buffer capacity. We ready?
Yes.
Okay. So to do buffer capacity, which is part B, I'm going to go with our modified equation, except for I'm going to modify it a little bit more, right? And there's really two ways we can think about this, and I've thought about like the best way to do it. So when we think about our titration curve, and we think about our buffer capacity, this is the buffer capacity, right? If we do it, and there's like 3 different ways we could do it, right? Our buffer is someplace here, so I could look at how much more HCl I could have and how much more NaOH I could have, right? And I can look at the 2 sides of that. I could look at it from the midpoint and say how much does it take to go each way. Or I could look at it in terms of how much to get there from the start, right? All 3 of those are valid ways to do a buffer capacity calculation. All 3 of them have their different pros and cons, but notice, ultimately, all 3 give us the same change in volume, right? All 3 of them still are going to give us the same change in volume for the buffer capacity. And that shouldn't be surprising, because buffer capacity is all about stoichiometry, right? Just how many moles of stuff are there. It doesn't matter where the equilibrium starts, because it's how much moles of stuff is there. So I can show you, my favorite way to do it is the way in orange, but I can go ahead and show you all 3 ways to do it. Realizing that our starting buffer, let's see if I can remember this. BH plus at excess, was that the 0.12, and the B at excess was 0.08. Or we could think about it, so that would be like doing it from the blue method. B at start is equal to 0.2. That would be doing it from the orange method, right? You're just doing a titration rather than thinking about, oh, I've got this buffer and I've got to adjust it. Like, technically the problem asks you to do it as if you're adjusting the buffer. But through this thinking, through this conceptual understanding, we can say, look, it's going to be the same no matter which way we cut it. I actually, just to prove it to myself, I did this calculation all 3 ways. I got the same answer every time. Now, it was, you know, I had to, if I do it for the method in black or the method in blue, I'm adding the numbers together. And if I do it for the method in orange, I'm subtracting the numbers from each other, because you're calculating this little bit and then the longer bit, and you subtract. So again, some conceptual understanding is necessary depending on which method we use, but they all come out with the same answer. I don't think there's a good way to do it for the black method from what we have. I guess you could do it if you wanted to do it in this method. You'd say BH plus is equal to 0.1 and B is equal to 0.1, right? That's the midpoint. So we can do it any of these ways. All would be based off of the Henderson-Hasselbalch and calculating 2 data points. The orange method is by far the easiest, so I'm going to show that one first or last? First. Okay. So if we're going to do that, we're going to do 2 different calculations. We're going to do 6.41 and 8.41. I had a lot of students who just wrote down the buffer range and said, we're calculating the buffer range, and that's not the same as the capacity. I had some students who said it's 50 milliliters because that's the point where the pH starts to change. That's the equivalence point. That's well outside of the buffer capacity. But actually, everything else, the setup is the same, right? I don't have to change anything for doing this problem if I'm doing it in this orange method as if I'm doing a titration. Calculating the HCl to 8.41 and the HCl to 6.41. And that's all I'm doing. So let's go ahead and do the 8.41 first. So I'm going to have 8.41. Subtract that, put it to the power of 10. That's going to be 1 to the power of 10. I'm going to have 10 is equal to let's just do 50, right? 50 millimoles minus V divided by V. That's going to give me 10V. That's going to give me 11V. I'm going to have V equals 50 elevenths. It's going to be 4.7 something. Did I do that right? That seems too easy. No, it's not. The power of 10, that's 1, that gives us 10. 0.2 times 250 is 50. Minus V, V, multiply V over, that gives us 10V. Add the V, that's 11V. What's 50 divided by 11?
4.55.
That makes sense because that should be our earlier point, our higher pH. It only takes 4.55 mils to get to that point. Let's go ahead and do the same thing, except for now we're going to do it for 6.41. 6.41 minus 7.41 to the power of 10. 0.1. 0.1 equals 50 minus V divided by V. That's going to give us V is equal to 50 divided by 1.1. 45.5. Buffer capacity's done. Just hands. Now keep in mind, because we did it in the orange method, I'm going to do my buffer capacity. I can talk about it a couple different ways. I can say it's 4.55 milliliters of HCl to 45.5 milliliters of HCl, or I could give the delta of the volume 40 milliliters. There's some rounding errors there and stuff like that, but it's... Wait, that's not right. I rounded too much there. 45.5 minus 4.55.
40.95.
That's better. 40.95 milliliters. That's the easiest way to do it. Would you like to see the blue method, which is probably the way that most of you attempted to do it? Working from the original buffer? I'm seeing a lot of no head shakes. Any yes head shakes? Okay. Yeah.
Is the buffer going to be on the quiz today? Or
Yep.
Is it, okay.
Yep.
It's like the entire 30
Yep.
minutes question.
Yep. 20 minutes. So, ready for part C? Part C, we do actually have to modify our Henderson Hasselbalch a little bit. Because part C asks, what happens if we add 4 milliliters of 1 molar sodium hydroxide? So I say, okay, what pH do we get? So I'm going to get pH is the thing that I'm looking for. And now I'm going to change this because I'm no longer doing it from the beginning. Well, actually, there's 2 ways we can think about this. I forgot to say this on the previous video. So, logically, I was like, oh, you just got to do this. But logically, if I made this buffer, this blue X, by adding HCl and adding about 30 mils of HCl, and I'm going to add 4 mils of NaOH, what is that chemically equivalent to? Just moving back. That's going to be chemically equivalent to just adding 26 milliliters of HCl at the start, right? Because that NaOH is essentially going to remove the HCl. So I could actually do this and then just say volume of HCl equals 30 minus 4. You could actually do it that way. And that would actually work, right? Because adding that strong base is equivalent to adding less acid at the start. That would be the easy way to do it, is just plug in 26 here and you're done. I didn't even think of that one until I was making the video. But the quote-unquote correct way to do it, I'm going to get rid of this so I don't get confused with what I'm about to do.
So is that an appropriate way to do it on the quiz then?
Yeah. Keeping in mind that the reason the milliliters worked out that way was because they were equal concentrations of titrant, and it was 1 molarity, right? We would normally think about it in terms of the number of moles, but since I gave you 1 molar solutions, the number of moles was the number of milliliters, or the number of liters. So the other way to do this is you would say pH equals 7.41 plus log. You're going to take your 0.08 times 250. So notice this is the amount that you have. If you do this number minus that number from the making of the buffer, this is your concentration of the made buffer. Divided by 0.12 times 250, that is the moles of the made buffer. Now if I'm adding base, do I subtract on top or add on top? Plus 4 times 1, that's the amount of base I'm adding. And if I'm adding base, do I subtract on bottom or add on bottom? Subtract 4 times 1. Solve. Now, before you even solve, if you remember from the video, the kind of like quick, kind of rough idea video I did, what was the volume to the midpoint? If it's 50 milliliters to the equivalence point, 25 milliliters. This is 26 milliliters. This is essentially the same as adding 26 milliliters. I'm expecting a pH that's almost exactly 7.41. Should be a milliliter past that, so maybe 7.4, 7.39. Yeah.
Sorry, where'd you get 4 times 1?
Because the problem specifically says you add 4 milliliters of 1 molar sodium hydroxide. Yeah.
Wait, so the first way you did it as a shortcut just because they had the same molarity?
Same molarity, so I could just think about it in terms of the number of moles change.
So this way it works regardless of what the molarity is?
Regardless of the molarity, right? And technically, you could do it that other way I mentioned, but you'd have to convert to the number of moles and then do an M1V1 to get back to the number of milliliters you essentially subtract, right? Because adding the opposite type of titrant, so this is a strong acid, so adding a strong base is essentially subtracting away the strong acid you added. regardless of the concentrations, you can do it in terms of number of moles. Yeah.
Can you just go over again why we're using the 0.08 times 250 on the top and not the
Yeah.
total?
So in this case, this is modifying from the buffer as it was made. So we have to look at, say, what was the buffer when it was finished being made? And that's where we had the 0.08 molarity for the base and the 0.12 molarity for the acid at the excess point after the reaction. So that's where this one is for starting at the very beginning, and this one is for starting here. So it's just that slight change, which makes me want to erase this one and change it to orange, and erase this one and change it to blue so all my colors match up better. But I could also just do this. Let's do this. Right, so I have to get this black X is that value, and then I'm just changing it backwards a little bit. Whereas this one in blue here would be, well, I did it. I want to do it in orange. I'll just leave the blue one as it is. But this black equation is equivalent to saying this is where I am, and I want to move back a little bit. So where I am is based off of those values. I guess that's how you do that one. Trying to look at how long we've been talking. Oh, that was 15 minutes, but could have been done much quicker. I was explaining a lot of things. We did the first problem 2 different ways. It can be done pretty quickly if we've been practicing. Other questions? Other things, I know you haven't seen the midterm yet, but if you can remember any problems, anything you want to ask about, anything from the homework. So we're going to do the quiz, and then we're going to do something fun, which is naming metal complexes. They're like the silliest, funnest names ever. They're really easy to do. They have a very straightforward mechanism for how you name them, and you get really goofy names. Dibromo, diaqua things. Bromo's a real thing. Okay, I'm going to go ahead and stop the video for now. We'll have that quiz later today. Make sure no questions.